Welcome back to Math 111. This video begins the first part of Chapter 7 on basic probability. Part 1 consists of an introduction to probability and random variables. Always remember to load the Mosaic and Tiger Stats package prior to starting your work. And let's get started. We've spent quite a bit of time in previous chapters discussing populations and samples. It is one of our goals in this chapter to use the language of probability to describe populations and samples. Secondly, we would like to learn to compute some probabilities as well. Probability is the numerical measure of the chance or the likelihood of an event occurring. The probability that an event occurs is always a number between 0 and 1. The word probability is commonly encountered in everyday language, but it can have different interpretations. The three interpretations that we will discuss are subjective probability, theoretical probability, and long-run frequency probability. Let's start with subjective probability, although this is the interpretation that we are least concerned about in this course. The probability of an event is called a subjective probability if it is based entirely on one's personal belief that an event will occur. For example, if a surgeon who is performing her very first surgery tells her patient that she feels the probability that the surgery will be a success is 0.99, she is describing a subjective probability. There's no way to mathematically calculate subjective probabilities. A subjective probability is very different from a theoretical probability. A theoretical probability is entirely based on reason or theory. For example, when we say that the probability that a fair coin lands heads when tossed is 1/2, we are describing a theoretical probability. Since theoretical probabilities are based on reason, we can talk about ways to mathematically calculate such probabilities. Let's clearly define a couple of terms first: sample space and event. Suppose you have an experiment that can result in various outcomes. The sample space is the set of all possible outcomes. For example, suppose the experiment was tossing one fair coin one time. The sample space for this experiment, a one-coin toss, would be heads and tails, because those are the only two outcomes of the experiment. An event is some collection of these outcomes. In other words, it is a subset of the sample space. So tossing a head would be an event in our one coin toss example. Calculating theoretical probabilities for events is easy if all of the outcomes in an experiment have the same chance of occurring. You just take the number of outcomes in the event and divide by the total number of outcomes in the sample space. Like in our one coin toss example, the only outcomes are heads and tails. This was our sample space. Since we are tossing a fair coin, the chance of the coin landing heads is the same as the chance that it lands tails, so we can use this formula to easily compute probabilities. Now, even though this example is very basic, let's see how it works. If we wanted to compute the probability that a fair coin lands heads, so we want the probability of heads, there is one outcome that corresponds to the event. That outcome is heads. There are two total outcomes in the sample space, heads, tails. So the probability that a fair coin lands heads is 1 divided by 2, or 1/2, or 0.5. Let's look at another example. This time, let's consider tossing a fair coin 2 times. The sample space is the list of all possible outcomes that may arise when performing this experiment. We could toss a head first and a head second, HH, or we could toss a head first and a tail second, HT, a tail first then a head second, TH, or a tail and then a tail, TT. Since the coin is fair, each of these outcomes has the same chance of occurring. So we can compute probabilities for various events. Suppose the event is that we toss 2 heads in a row. There is only one outcome out of the 4 in the sample space that corresponds to this event, HH. So the probability of tossing 2 heads in a row is 1 divided by 4, or 1/4, or 0.25. Let's do another. Suppose the event is that we toss one head. There are two outcomes out of the four in the sample space that correspond to this event. HT, heads then tails, and TH, tails then heads. So the probability of this event is 2 divided by 4, or 1/2, or 0.5. The probability of tossing 0 heads is the same as the probability of tossing 2 heads, because there is only one outcome in the sample space that corresponds to this event. The final interpretation of probability that we are interested in for this class is long-run frequency probability. A long-run frequency probability is computed by knowing the proportion of times an event occurs when an experiment is performed many times. To compute it, we take the number of times the event occurred and divide by the total number of times the experiment was performed. For example, suppose that a coin that is tossed 1,000 times lands heads up 502 of those times. The long-run frequency of the coin landing heads is 502 divided by 1,000, or 0.502. You may have noticed that the long-run frequency in the previous example was different than the theoretical probability that a fair coin lands heads up. If the coin in the experiment was fair, we would see that the long-run frequency probability gets closer and closer to the theoretical probability as we perform the experiment more and more times. In other words, while these two probabilities may never be equal, the long-run frequency is a good approximation to the theoretical probability, especially if the experiment is done many, many times. Let's move on to random variables. This is often a difficult idea when first encountered. Don't let it be confusing. Very simply put, a random variable is a variable whose value is the outcome of an experiment. Okay, so you might be thinking that sounded confusing. So let me try to clarify. Previously, when we were talking about probabilities of events, our notation was a little bit cumbersome. Remember how we described tossing one head and two tosses of a fair coin as either HT or TH, heads tails or tails heads? We could make this description easier by talking about this event in terms of a random variable. For example, we could define the random variable, call it capital X, as the number of heads in two tosses of a fair coin. Then, what we are trying to compute is really just the probability that capital X equals 1. So we're computing the same thing, we're just changing the notation to make life a little easier. Now there are a few details that should be mentioned. Random variables are typically letters near the end of the alphabet, like X, Y, and Z. Whether or not we use capital or lowercase letters depends on whether the experiment has already been performed. Prior to an experiment, a random variable can take on various appropriate values. Some values are more likely than others. This will make more sense if we look back at our coin toss example in more depth. So, we're tossing a fair coin twice. Let's stick with the same random variable I described in the last slide. We'll let capital X equal the number of heads tossed. We've listed the sample space that we talked about before so that you can compare this to the appropriate values of the random variable. Since we're tossing a fair coin twice, we could potentially toss 0 heads, 1 head, or 2 heads. Those are the only values that the random variable X can assume. This is the range of X, 0, 1, 2. Since the set of values that this random variable can assume is a set of whole numbers, we call this random variable a discrete random variable. We'll talk about continuous random variables later, but for now, just keep in mind that the distinction between discrete and continuous is like it was when we were talking about discrete variables versus continuous variables. So again, a random variable is considered discrete if its range consists of integer values. Okay, so let's compute some probabilities using random variables. We've already talked about the probability that X equals 1. This is just the probability of tossing one head and two tosses of a fair coin, HT or TH. As before, this probability is 1/2. Again, the idea is the same. All we've changed is the notation. The probability that X equals 0 is the probability that we toss 0 heads and two tosses of a fair coin, which is the same as the probability that we toss two tails, TT. This is 1/4, or 0.25. Likewise for x equals 2. So the random variable x can take on any value in its range, although some values may be more likely than others. In this example, x equal 1 is more likely than x equals 0 or x equal 2. We can do a better job of organizing and displaying all of this information. The probability that the random variable, capital X, equals the value, little x, is called the probability distribution function, or PDF. Since little x can take on various values, probability of x equal little x is a function whose input is the value of little x and whose output is the probability. In other words, the PDF assigns probabilities of all of the values in the range of the random variable. Again, an example is helpful here. Let's return once again to tossing a fair coin twice. We can view the PDF as a table or as a histogram. Let's look at it in table form first. The first row is the values that little x can be. The second row is the probability that the random variable, capital X, takes on those values. So for this example, 0, 1, and 2 make up the first row because those are the values in the range of the random variable. The second row should look familiar to you. These are the corresponding probabilities. So for example, 0.25 is the probability that capital X takes on the value 0. 0.5 is the probability that capital X equals the value 1, and so on. The same information can be displayed in the form of a histogram as well. Notice that the bars in the histogram are centered over the values in the range of the random variable x. The height of the bars correspond to the probability that the random variable x equals those values. So the bar centered over 0 has a height of 25%, or 0.25, just as we saw in the table. One detail that should be noted is that the probabilities in the second row of the table PDF should add up to 1. A quarter plus a half plus a quarter equals 1. Likewise, the areas of the bars in the histogram should add up to 1. The width of each of these rectangles is 1, and the heights are the probabilities, so the area of each bar will equal the probability. So 25% plus 50% plus 25% is 100%, or 1. We can visualize probabilities using the PDF, either table form or histogram form. For example, the probability that x equal 1, being 1/2, can be seen here by this column highlighted in blue in the table, and can also be seen as this middle rectangle shaded in pink. The probability that x is greater than or equal to 1 is the same as the probability that x equals 1 or x equals 2. This is the sum of the last two columns in the PDF table. 0.5 plus 0.25 gives us 0.75. In the PDF histogram, this is the right tail shown shaded in pink. That's it for part 1. In part 2, we'll discuss expectation, standard deviation, and a special type of discrete random variable. Thanks for watching.